Okay, we're going to continue to think about calorimetry. This is our second video in our enthalpy and calorimetry lesson. I'm going to call it 3.3b. I might have called it 3.2 in the other one, but we're in the third video set for this unit. So we talked in the last video about our heat transferred, and this is a small letter, so it depends on the path, is equal to the specific heat capacity of a substance, that's a unique property of a substance, times the mass that you have, times the change in temperature. Now, so this is just heat transferred. We are now going to relate our heat transferred to our enthalpy change. And our enthalpy symbol, our enthalpy change would be delta H, because our symbol for enthalpy is just the H. And we said before that, in a previous lesson, that our delta H, if the outside pressure stays the same, if we're at constant pressure, our change in our enthalpy will be equal to the heat transferred. And I'm going to put a little p here for that because that's at constant pressure. So we're going to use this relationship that you have on another page of notes. Our change in enthalpy for a reaction, when we talk about enthalpy, we're usually at constant pressure, we're usually talking about a reaction or a system that's doing something. And that change is going to be equal to the heat transferred. So what does that look like for us? You have a similar picture on your page. This is a calorimeter. And a calorimeter is something that you use to measure heat transfer. You could write that down, that definition. It's just a tool used to measure heat transfer because calorimetry is the measure of heat transfer. And so here we have two styrofoam cups. We might actually use a different type of calorimeter, but we might use, when we do our lab ones, made of styrofoam cups. Styrofoam is very insulating, so it holds the heat in. Heat does not transfer easily. Heat does not transfer easily through the styrofoam. And we have some water in here. So we can measure the heat transferred to or from the water. And we would use our equation, heat transferred, this is for water, is going to be equal to the specific heat capacity of the water times the mass of the water times the change in temperature of the water. And we can use this thermometer to measure the change in temperature. So if we somehow add heat to this water or we take away heat from this water, we can measure it because we now have relationships and an equation to do that. Well, now let's think. We've put this water in two styrofoam cups, so it's not likely that heat's going to be coming in from the outside. Okay, this is not likely to happen. And it's not likely that heat's going to be just spontaneously leaving. I don't think I can erase these arrows now. Oh, I can. Great. I figured out what makes me stop erasing. I can't erase once I hit the pause button. Okay, so what's going to add heat or remove heat from this water? Well, if we put a reaction mixture in our cup, if we put some atoms and molecules that will react with each other, and you actually have that in your diagram. So I'm going to draw, this is going to be our reaction mixture. So we're going to add something to the water that will react. When that reaction takes place, that reaction will have an enthalpy. It will have its own change in enthalpy. It will either, the reaction being the system, the reaction is the system. Let's write that down, system. The reaction will either lose heat and be exothermic or gain heat and be endothermic. So if my system, which is this black ball here, that's where the reaction is happening, if that loses heat, where is the heat going to go? Correct. The heat's going to go into the water. If the heat goes into the water, what's going to happen to the temperature of the water? It's going to go up. So, I didn't leave myself a lot of room. Oh, I'll just make the whole thing smaller. How's that? Okay. So, if our reaction, our system, loses heat, that would mean our delta H, our delta H is negative. And where's that heat going to go? That heat's going to go into the temperature of the water. It's going to cause the water to have a change in heat content, which I can measure using this equation. So my change in my heat from my reaction, because all that heat will go into the water, that's going to be equal to the heat gained by the water, assuming my reaction loses heat. So if and now we're going to think about this from a sign perspective. If this is exothermic and this is losing heat, all that heat's going to go into the water, but this side's going to be positive because it's gaining. So your order of magnitude, if we put these in absolute values, the amounts would be the same. But we're not going to put it in absolute value because I can't have a negative equal to a positive. So to make the signs work in this equation, I have to say that my enthalpy change in my reaction is going to be equal to the opposite of my heat gained by my water. So we're going to, and this would work just as well if my delta H was positive, and if this gains heat, it will still be equal to the opposite of the heat lost by the water. Because if this gains heat, if heat goes into my reaction, where's that heat coming from? It has to come from the water, so therefore the water would have to lose heat. So your amount of heat gained or lost by your reaction is equal to the amount of heat gained or lost by the water, but if one is exothermic, the other has to be endothermic, because if one is gaining heat, the other has to lose heat. We're going to work a problem for this. And when you listen to the next problem, this whole concept would work the same. Let's make this a little bit smaller. We don't have to have a reaction going on in here. If we have a calorimeter, and we have water in here, and we have a thermometer, and the water is at one temperature, and then I should use a blue for more water. If I add more water from another source, and this water is at a different temperature, these two amounts of water, the water that I had and the water that I add, once they're all in the same cup, they're going to come to thermal equilibrium. Eventually, they'll be at the same temperature. The water that was in the cup will have absorbed heat. Well, it depends on which is hotter, but they will transfer heat. So the heat lost by one amount of water will be equal to the opposite of the heat gained by the water, the other amount of water, once you put them together. That's the type of problem that I'm working in the next slide. So, and I think it's the same, hopefully, as the one on your paper. Okay, so a 100-gram sample of water at 90 degrees Celsius is added to a 500-gram sample of water at 10 degrees Celsius. They ask us the final temperature of the water. Okay, so here's a clue. First of all, it's going to be between 10 degrees and 50 degrees. It's not going to be exactly between, and it's not going to be, it's going to be between 10 and 50. We're going to calculate it and see why. So we have, we're asking about temperature. Water is changing temperature, and we have an equation. Oopsie daisy, what's going on here? Actually, let's give ourselves a little more room. This is so cool. So we know that, come on, pen, why aren't you writing? Apparently I was writing, but I was writing in white ink. Okay, so we're talking about temperature, and we know that heat equals mass times specific heat times delta T. Okay, and we have some water. Let's make this blue. Okay, so we have some water, and then we've added some more water. Okay, so we have the heat from the water that we had, which is here, and we have the heat here. So we're going to have heat lost by the water that was at 90 degrees, and that's going to be equal to the heat gained by the water that was only at 10 degrees. So let's write our formulas out. The heat lost is equal to mass times specific heat, and remember, we already said that the specific heat of water was 4.18 joules per grams degree Celsius. And that's going to be by the change in temperature, and that's going to be equal to the mass of the water that gained the heat times the specific heat times the change in the temperature. So I'm not doing what I usually do, which is writing down everything we know, but we know that our water that's at 90 degrees, which is what's going to be losing the heat because it's at a higher temperature. Okay, so we're going to rewrite. We have minus 100 grams, and I said minus because it's the opposite. This is lost, this is gained. One of these is going to end up being negative, and so in order to make it equal, you're taking the opposite. We can talk about that tomorrow. Times TF minus 90 equals 500 grams times TF minus 10. And then to solve this, we use algebra. We're going to distribute. I'm going to do... Okay, I jumped ahead on the algebra. I distributed my 100 to TF and 90, and I distributed the 500 on this side to the TF and the 10. I had minus 100 times TF plus 9,000, which is 100 times 90, equals 500 times TF minus 500 times 10, which is 5,000, so I have 14,000 equals 600 TF. I divide both sides by 600, and I get my final temperature, which is TF, is equal to 23.3 degrees Celsius. So that is how you would find the final temperature.